Our next speaker is Dr. Luigi Cavallo. Sorry for my presentation, I'm sure it's... Anyway, so Professor Cavallo is a professor of chemistry here at KAUST. He got his PhD from the University of Naples in Italy. And today he will be talking about multivariate linear regression workflow for catalysis design with a few entry data sets. Okay, when you're ready, you can start.
Okay, thank you for the introduction, and I want to thank Thibaut and Manny for inviting me to present our results here. So this is the title, and going to the point. So this is the outline, brief introduction to set the problem, then the model we developed, and then how we applied it to our case study and concluding. So catalysis, familiar to some of you, not all, but basically we transform reagents into products. Of course, we want that the products are higher value compared to the reagents. And we know many things about the good catalyst. A bad catalyst is give you a mixture of products, so you have to separate them. The good catalyst gives you the specific product you're interested in. We know some other keywords, selectivity, stability, sustainability, so we know a lot. So why it's so difficult to develop new catalysts? Because mostly we are using the trial and error approach, which means we know what we want, but we don't know where it is. And this is a disorganized organization of catalyst space. Maybe sometimes we were working on this system. A small modification of the catalyst could have given a wonderful catalyst, but we didn't know, we were blind, and so we moved away. Of course, if we have something like this, life is much easier. We need a matrix descriptors to reorganize the catalyst, and if we are here, we know in which direction we have to move. So, the role of computational chemistry in catalyst design. For many years, quantum mechanics in the variation of density functional theory has been the workhorse of developing and understanding catalysts. DFT can offer a wonderful mechanistic understanding, and if you want to fine-tune a catalyst, there is no better approach. Just to give an idea, with the explosion of DFT in molecular catalysis, I think was with this catalyst during the metallurgy revolution in the 1980s. But as limitation, it's a slow method and too slow for rapid screening, which is making not at the pace of the advancements of the experimental hardware. Still, it's very useful today. This is an example of reaction which is being highly developed today. It's photoredox catalysis, extremely complex because you have radicals, you have excited states, and if you don't use DFT to rationalize this chemistry, it's extremely difficult. Now, the future lab, we can imagine this, where we have a machine learning station which will tell us to an automated experimental station. Out of these 100 systems, just test these 10, these 90 probably are useless, and the automated robots will test the 10, and then will eventually produce better catalysts, or will give a feedback to the machine learning station to improve its understanding. So, again, in molecular catalysis, in a way, this is not completely new, because in the pharma industry, the so-called QSAR methods are known since 50 years. So, it's not new. Of course, they were using mostly linear regression method. So, let's see which is the status of the art in molecular catalysis when we have the large data sets. This is a paper in Science 2018, cross-coupling reaction, 4,000 reaction, and you can see they were using, I think in this case, we're using a random forest model where they were able to correlate properly experimental data with predicted. And the year later, 2019, Scott Denmark, another organic reaction catalyzed by molecular catalyst, altogether 1,000 reaction, and they were able to use the violet point, purple point, to predict the behavior with reasonable accuracy of the red point. And it's important here that the red points are out of the training performance in training set. Still, some problems. Achieving 1,000 experiments in molecular catalysis requires a huge amount of time and investment, because you have to synthesize the single catalyst. And also you need robotic hardware, which is expensive. So if we go for this approach, this means that we are developing, and for sure we have to do it, a wonderful machinery, but this is out of the reach of most of the lab around the world. And for me, one of the keywords of science is democracy of science, which means everywhere in the world we can do some experiments. And another drawback, if we analyze better this 4,000 reaction, we understand that they were using only 4 catalysts, and the catalyst, the key component to give results, together with 27 additives, which mean solvents, an organic salt, something else, and 15 substrates, which is the scope of the reaction. This is the way they arrive to 4,000. Denmark, 43 catalysts, multiplied by 25 substrates, this is how they arrive to 1,000. And this clearly indicates that the number of molecular catalysts is small. And this was realized in the field, and Matthew Sigman has done a lot of work trying to see, can we play with small? And when I say few entry data set, I really mean few. And this is a kind of work, and you can see that hollow diamonds are predicted well using the black square as training set, even something just out of the training data sets, and it's a promising tool. Of course, we should understand, I believe, if this kind of approach can be used to predict something which is here, and we have to understand, I have a new model, I have a new data set, I develop a model. Can I trust the prediction of this model, or they are useless and better I do something else? So we went trying to do this, we downloaded the scikit cheat sheet, we started, we arrived here, less than 50 samples, get more data. So basically, we are out. That was the story. And to enter into the regression domain, you need a lot. But still, in the field, we don't have, most of the cases, 50 cases. And taking inspiration from our slide yesterday, and this is the current state of the art, you are basically here. Unfortunately, I'm here. That is the status. And so we have to play with this. Why this? Because synthesizing this molecule, it's a nightmare. You have many steps. Every time you have to purify the reaction outputs, and you have to see if you can make it, and so on. So with only a handful of data, can we make robust and statistically meaningful prediction? That is the goal. So the goal is to develop a protocol which allows to identify outperforming catalysts with a few entry data sets. And I will show, we will assemble a large database, we'll try to develop models, we try to test if this model, and most importantly, I will try to derive so-called confidence score. So you have a new data set, you develop a model, you calculate some parameters, we compare with the confidence score we have derived, and you can say, okay, it compares well, I can use this model for predicting outperforming catalysts. And to show the whole story works, we applied it to a specific case. So developing the model, what we did, we assembled 29 classes of reaction for altogether more than 500 reactions from literature. And that means 29 small data sets, on the average 18 reactions per data set. The range is 10 to 44. We try to be broad, different chemistries, so we have activity, reaction yield, various semi-selectivity. It is a first view of the reaction we considered, and we were englobing 20 metal catalyzed reaction, 8 organocatalysis, and 1 metalloenzyme. This is the whole story, so covering most, I would say, of the chemistry around. And for each of the 20 reaction class dataset, we have to develop a specific model. We tried to develop a model from literature if possible, otherwise that was not possible. It was too long. Okay, some technical detail. We stayed at the end in ordinary least square. We tried something else, also Gaussian processes, but we didn't see any clear benefit from using other tools. So the model is basically this one, very simple, linear combination of electronic and steric descriptors. just remind, electronic descriptor means that are able to capture a phenomenon which occurs through moving of electron density through the bonds. So electron density moves through the bonds and you have the electronic effect. Steric effect is much more simple. It's simply space occupation. One ligand is large, the other ligand is small, how much space they take. Now, in literature, there are about 2,000 descriptors, which, I mean, we could make another presentation on these descriptors. But give an idea of many models you can develop. I just focus a bit on the steric descriptor because we found it to be one of the most important parameters for rationalizing reactivity. And one first steric descriptor is the metal center. This is the ligand, which stays on the metal all the time during reactivity. And we quantify the steric hindrance of this ligand as how much of the first coordination sphere around the space, around the metal, is taken by the ligand. So more space is taken, the larger is the ligand. And we see here, for example, this is a typical size of the first coordination sphere and different phosphines. But we also realize that this first coordination sphere is completely missing to understand what's happening in this region here. So we developed two regimes, two ranges steric descriptor. One is the first coordination sphere, and then the second is this spherical shell. And now you can see that if we look at the spherical shell, we can make a clear difference between the two systems. Of course, we need to define this radius and this radius because they are empirical parameters at the end. So 29 reaction, I show one example, which is reaction number 12. And this is a cross-coupling reaction published by Doyle in 2017. And she was trying to improve the yields of this reaction using 17 different catalysts, which correspond to 17 different phosphines bound to the metal. So these are the phosphines. They did also some kind of correlation, regression, and they developed this model, measured yield, predicted yield. You see it's a quite good model. And R square is 0.96, Q square 0.88, with a 4 descriptor model, including a cross term. We started working on this with a simplified model, only one electronic descriptor and two steric descriptors, the coordination sphere and the spherical shell. And we had to vary the radius because the radius is a fundamental parameter. So we were varying the first sphere between 3 and 8 angstrom, the spherical shell between 0 and 5, and for each pair of these radii, we calculated the R square. So we have this heat map where there are more than 2,000 pairs, and we identified this point here, these specific values of R1 and delta R, as the best value. And it's clear that if you miss to get the right pair, you get poor performances. With other model, we got R square, Q square, R square similar to Doyle, Q square slightly better, and we don't have cross terms. Other insight that you can get, trying to compare good versus bad performing catalysts by increasing the radius of the first coordination sphere. And in green, we have the top performing catalyst, and you see that all along this change in the first coordination sphere, the three top catalysts, they're barely the same profile. Instead, if we take the poorly performing ones, you see it's completely scattered. So they are identifying already something. And then if we make kind of projection on the first coordination sphere and the spherical shell, you can see that the top catalysts are clustered in a specific region. Then if you want to have a better fitting, of course, you need the electronic descriptor. So we were doing this kind of analysis for the 29 reaction data sets, and now just going to overall results. This is the results of all the data together, the fitting, and adjust R square, 0.90, and the mean absolute error from the experimental data is 0.22. Leave one out, cross-validation. Of course, there is a degradation of performance, but I would say still excellent. And here we use this to start setting what we call a confidence score. What it means, if I have a new model, I would like that the new model will perform with this value here. And we will see later why I think these are a good estimate to say if you are above this, you are doing well. So this 4 confidence score. Then another property that we noticed is that when you have a small data set, chance correlation is very likely, which means, so we had to test for it. So how did we test it? With the randomization of Y randomization. So this is the original data set with all the properties ranked here. Then you create a scrambled data set where the descriptors are the same, but the properties are scrambled. And you ask the model, can you rationalize this? Of course, you hope that in no case the scrambled data set will perform as well or even better than the original one. That would mean chance correlation. And we were doing this kind of scrambling 1,000 times for each of the 29 reaction data sets. And to compare all the data in a single plot, we scale the original R squared to 1. So all the scrambled should be below 1. And you can see that we can make a separation between 2 classes. The red point, they stay quite below 0.1. But the green points, instead, in too many cases, especially when the Pearson correlation with the original data is small, they are really close to 1, which means this green point corresponds to reaction that the chance correlation is high. So to define confidence score here, we just used the red data, and we have that to exclude the chance correlation, the R square max should be less than 80.8, and the average below 0.25. Then another point, with small data set, you don't have stability in the fitted line. It might be that as you change a bit the training data set, the fitting line tilts a lot. So to understand if the fitting line is stable, we use a classic bootstrapping procedure, which means the original data set, we removed 3 for testing, and we created a new training data set, same size as the original one, which of course means we have to have some duplicates because we have to compensate for those in the prediction bank. And we were doing this loop 1,000 times for each of the reaction data sets. And then we were comparing how much is the deviation of the coefficient of these bootstrap bags from the original one, and then the same for the fitted data. And you can see that in both cases we have quite narrow distribution, which means, of course, it oscillates a bit the fitting line, but it does not that much. And this allows to introduce 2 more confidence scores, which is the MIA on coefficients and on the fitted data. So far, we were using training data set and doing something within the data set for prediction. But the real goal, as I was saying, we train here, and we want to predict here, which is totally different from, I would say, image recognition, where I draw a number, and the number will be between 0 and 9. There is no story. Here, we want to understand new numbers. So we want to train here and predict here. How to know if your model can do it? Again, approaching using literature is that you rank first from low to high performance, and then you make this kind of splitting, and you train here, and you see if you can predict the top catalyst. We were doing this with variable splitting. As you can imagine, increasing the splitting, the performance of the grades. It's unclear if it's degrading because these are more difficult or because we start with small data set. If we remove 30% of the data, the training data set becomes even smaller. So it's too small data set. But anyhow, this is the final between the predicted data, the 8%, which correspond to this one. And you can see that in most of the cases, we are able to capture the right trend. There are a few points here, and actually they correspond to one specific reaction data set, which was completely gone wrong. So, and this is linear learning curves. You can see that up to 20% of prediction, more or less, the mean absolute error from experiment of prediction is quite stable, but then it starts to move. And so we use at this point as another confidence score, MIA 0.80. So, optimization. We were said, okay, let's simulate a real-life experiment. What it means. How to do this? We have the original data set, again, split 80 to 20. Then we removed 3 catalysts from the bottom one, 3 catalysts from the top one, and this is the first training data set, which is the original training data set, removing these 3. And with these 6 catalysts were assembled into 3 prediction bags. So what we did then? We went into optimization loop, which means we start here with the training data set, which is this one. We train a model, we predict the first bag, and if one of the system is predicted to be high performance, it means we make the experiment, so we can add it to the training data set, and we go to the second bag, and then to the second bag every time we refit the model. And we can use here for understanding how the performance using a collecting data section, where we have high performance predicted, yes, so compared with the experimental performance. Is high, yes, so it's marked as true positive. Then we predicted high performance, but the experimental performance is not high, it's a false positive, because these 2 will be suggested for an experimental test. Of course, we can do the same in case the model is saying this model has low capability to predict, should perform poorly. So true negative, false negative, true positive, assembling all together. Now we have to decide how we define a prediction as a high prediction or not. The first idea was, okay, we set this threshold to the top system in the training data set. If you are right of this threshold, the prediction is marked as high performance. If it's left, it's a. But we found out that since there are errors in our prediction, some system here were actually predicted in this zone. So with this rigid threshold, we were missing too many systems. So we introduced a buffer, which means moving the threshold a bit on the left. And if we have a 90% cutoff, which means we have 90% of the threshold in the training data set. And with this, we calculated all the data, we assembled, and we get classic precision, accuracy, and recall as a function of the cutoff. So 100 means that it's sharp at the training data set. You can see that if we focus on precision and accuracy, there is an improvement as we allow for this buffer, but not that high. The biggest impact is on the recall, which is our capability to take and predict a system as high performance correctly. So taking all this data together, the conclusion is that if we work with this 80% catalyst, if we suggest 10 catalysts for experimental tests, roughly 6 to 7 should be outperforming compared to the training data set. And these 3 values were used as 3 other confidence score. So with this, we went searching for a case to apply the story, a bit late. So polymers, we live in the polymer age. Polymers is plenty, this room is plenty of polymer, it's important to the market, let's go to the point. We have the industrial catalyst, and one fundamental component of this industrial catalyst is a Lewis base as a donor. If you have the wrong Lewis base, you get low quality and no yield. So you have to choose this properly to get high yield and high quality polymer, high grade. These donors are molecules that have 2 oxygen normally, and this oxygen can coordinate on the magnesium dichloride, which is the support of this catalyst. So why we focus on this? Because we found this patent in the literature where they were testing 18 different donors, 18 carbamates, yields between 15 to 80 kilogram of polymer per gram of catalyst. Industrial target is 120. So there is range for improvement, and we decided to go for this. So this is the model we used to derive all the descriptors, and we tested different cases, 1, 2, or 3 electronic descriptors, always with the steric ones. All models, we had a lot of good models, so we decided to get a consensus. We take the 10 top and we average results. So, performance of the model on the 18 system in the data set, blue line experimental, red line what we fitted in the model, and green from leave one out. And you can see that performance of the model is really good, except maybe for this case here. And then for this, we calculated the scores we have seen before, and we compare with the confidence score that we get from the 29 reaction data sets. And if the score performs better, it's positive in this case, and you see that all the scores we calculated are all better for this model to compare to the average of the 29 reaction dataset, except for one. But we said, okay, this is probably a good case we can try to predict. And so we decided together with the experimental partner to design these 10 catalysts, did then Lewis bases. Again, synthesizing them is not that easy. And we first predicted them, and these are the green bars, and then they went to the experiment to do the experiments. We decided to make them all, because we also want to see if by chance we predicted wrong, and then instead you have boom, very high, which means if you say something wrong, it has to be wrong. And you see there is a very good correlation between our prediction and the later experimental tests, and even one of them, it's even slightly better than the best catalyst, the original data set. So we said, okay, let's move on modification on this one, which is this, and we decided to focus on this group here, and this is the result of the second cycle, changing the steric of this group or changing the electronics with the analogen, and all of them were predicted good, so they were all tested, and the second cycle, the results are here. Again, you see that the green bar says test it. And eventually we were lucky because one of them, it seems to be really outperforming the training data set. So the main point here is that we tested 14 catalysts, and according to our prediction, we would say to the experimentalists, these 7, forget, because our prediction said they will not be bad. Test these 7. And out of these 7, one is really good. We were not well at predicting this, but again, it's kind of a classification, yes or not. We say, test this. The good one should be here. Do not test them. And means saving 50% of the experimental work. And with this, I conclude. So we play with really 20, 30 catalysts at the time, but still this model can be used. And we also, I think we have derived a full protocol to test if a new model can be used for prediction by calculating scores and comparing with the confidence score from the overall data set we assembled. Again, very easy to use, many data, which goes back to the story. Basically, any lab in the world can use it, provided they have, let's say, 20 catalysts having in hand. And with this, I conclude. I want to thank KAUST, because he programmed all the pipelines for doing this test, and Laura Falivene that was fighting with these 29 reaction data sets, and the experimental partner that decided to follow us and do the experimental tests. But today, most important to me has been your kind attention, so thank you so much.
Thank you very much. Do we have a question there?
Thank you. Interesting talk. I wonder in your model for property prediction, you put something for sterics and something for electronic, and then I think maybe the process parameters you didn't include, like temperature, pressure, solvent, etc. So I don't know how you count for this.
I mean, this is a good point. First, if you have this data set, which is small, you assume that all the reaction conditions are the same. Because if you start moving also the reaction condition, that then becomes too much. And I can say more. If it is better if the same experimentalist is doing the experiment with his own hands. If you start collecting, because we tried to collect data from literature, a paper in 2016, a paper in 2018, a paper in 2020, to have a larger data set. We can fit the single papers, but when we combine the 3 papers together, it starts a mess, even though they should be mergeable. About selecting descriptors, there are many. Of course, that comes with experience. For sterics, today we always start with our own descriptors, because we have seen they work in vast majority of the cases. For the electronics, it's really, you have to try some of them because they change from case to case. But again, by experience, you know, there are 2,000, but you can start with a set of 20. And if you are happy, you stay with the model. If you are not happy with the performance of the fitting, you try to improve.
Maybe, yeah. We had Amir first. Oh. Okay, go ahead.
Thank you, Professor, for explaining us a lot of things. I'm not a user of AI. I'm rather a learner of AI, but...
Sorry, can you speak louder?
Yeah, do you hear me?
Yeah.
So, after you explained everything, I came to understand that you gone through a lot of refinements of the model that you try to do, because I feel that, or maybe it's, I want to take your opinion that for a chemical oriented process, which involves a lot of chemistry, a lot of parameters which can be fluctuating a lot, how tough it can be to get a stable algorithm. Because you know that the results that we get from maybe one simulation or one iteration, it can affect some parameters which can change a lot for the next iteration. In that case, I think it would be very, very tough in terms of time investment and also maybe cost investment to get a stable algo to actually make it 100% or 98% accurate. So should we just pretend that, yeah, there could be some kind of inaccuracy in this kind of chemical or chemistry oriented processes? Because a lot of people just doubt the accuracy of AI. So what is your opinion about the things that I just tried to express to you?
Yeah, if I got properly, our work today is just focusing on the catalyst. Of course, you can couple this catalyst together with the reaction condition with additives, and it goes in line with the work already published by Doyle and other people, Denmark and other people. Yeah. In that case, of course, you can inflate, let's say, the data set, because if you have additives, immediately you start increasing. But in this moment, we want to focus on one specific point. Of course, our model can be integrated together with the larger model, which is including temperature and other parameters of the reaction.
Yeah. Okay, thank you. Because, for example, even to a catalyst to work, it will involve a lot of reactions, and that can affect the variation in the results.
Sorry?
I'm not sure you're able to hear me. I was just saying that reactions that are involved for a catalyst process, that will also affect a lot in the accuracy of the results.
Yeah, I said, it's you have to go case by case. And our scope here was exactly this. If I have a new case, I develop a model. Can I trust the model? This is the question, not simply I develop a model and I use it. That was the scope.
Here, nice talk, Luigi. You talked about the scarcity of experimental data, which is hindering some of the progress. But in the beginning, you also talked about DFT, which is something that you do a lot. Have you looked into combining some calculations from DFT and using that to expand the data set? That's number one. And number two question is on the descriptors. You used, I think, 4 descriptors. In some other fields, I've seen people are using hundreds of descriptors for defining a molecule. So I was a bit actually surprised and maybe happy to see you can only work with 4 descriptors.
2 very important points. The first is about expanding the DFT, with DFT, the size of the data set. In principle, this is possible, but you have no clue if it will work. I can tell you that we are now working on a case where they were asking us, can you predict which ligand gives high enantioselectivity by DFT? We made all the calculation and we identified 2 catalysts that in principle should go high enantioselectivity. They tested them experimentally and the yield was extremely low. So having a full picture of the reactivity by DFT still is extremely complicated. The most difficult parameter is activity. Activity yield, basically, they go together. And anti-selectivity, if the catalyst is active, we are good. Various type of selectivity, regioselectivity, diastereoselectivity, and anti-selectivity, DFT is extremely good. When it comes to activity, DFT is weak, still is very complex. So, of course, if you have experimental data, you know they work. And then the second question is, if you have 20 data, of course, you can start with 50 different descriptors. And then you start building the model slowly. You try all combination of, let's say, 2 descriptors, then all combination of 3 or 4 or 5, and you see how the model improves, keeping in mind that, of course, if you have more descriptors, R square will be higher. So it's much better to focus on adjuster R square, which balance this. And there are also techniques you can plug in them all and ask the algorithm, chop down to only those which are relevant for the model.
Thank you. I know there are other questions, but we are a bit late on the time, so thank you again.
Thank you.
Now we have the coffee break.